When we talked about partial differentiation last time, we talked about how, just like with ordinary derivatives in the single variable case, you can use it to get information about instantaneous rates of change of a function as x changes or y changes. But today we're going to focus on a different use of partial derivatives. So first I'm going to, as I have been often recalling from the single variable case, the tangent line of a function at a particular point x naught has this equation: y is equal to f of x naught plus f prime of x naught, x minus x naught. And related to that, we define this function, and in Stewart it's written as just L of x. I'm putting a subscript f in here to indicate that this is something that comes from the function f. And this function, which is defined using the right side of that equation. This function is a linear function, so we call it a linear approximation, or a term I will use more often, linearization of f at x naught. So this shows one of the important uses of the derivative, that it's used to take any function and approximate it by a linear function, which is very important because linear functions are the simplest functions to work with. So there are a lot of cases, especially in like higher level applied math, where a function is replaced by a linearization around a point, and so that approximation comes in handy. Now graphically what's going on in the single variable case, here's f, here's x naught, here's tangent line. So here's a graph of f of x, and here's a graph of the linear approximation. Of course, at this point, of course, they agree exactly. As long as you're pretty close to x naught, it's still a decent approximation. Naturally, once you get further away, it's not so useful. If you want to approximate a function elsewhere by a linear function, here at x1, then you would use a tangent line around that point. So the choice of x naught is important. It indicates where this approximation is actually going to be valid. Now, how valid it is depends on f. So if you have a function that is behaving like this, and you want to linearize it right here, well, that's not a very good approximation, even if you're fairly close to x naught. So here, the error is somewhat larger, even though you're close in terms of x. But a function that, because what's happening here is the slope is changing fairly rapidly. The slope is roughly 0 at this point. It becomes positive here and becomes negative here. Whereas this function, quite steep, slope isn't really changing all that much. It's not so dramatic. So tangent line is a better approximation in this case. You can wander further away from x naught and still be fairly close. The value of linearization is still pretty close to the value of the function. But no matter what, as long as the function has a derivative, if you're close enough to x naught, you have a decent approximation of f by a simple linear function. Now, all of this is a one-dimensional case. Now let's go to two variables. This is a portion of a graph of a function of two variables. Z is equal to f of xy, and we have some point, x naught, y naught. We'd like to approximate this function linearly near this point. Well now, because we're dealing with two variables, we're no longer going to have a tangent line, we're going to have a tangent plane. So, because that's going to be the graph of a linear function of two variables. And we would like this tangent plane to have some of the same properties in the two variable case as a tangent line does in the one variable case. For one thing, the tangent plane must agree with a function at that particular point, at the point of tangency. Second, if we make a change in x or y, then the rates of change with respect to x or y for the plane should be the same as the rates of change of a function. So as long as we have those properties, then it's quite analogous to what we have for a tangent line. And in fact, the equation for a tangent plane is a pretty straightforward generalization of what you see for a tangent line. So given a function of two variables, the equation of the tangent plane at x naught, y naught is the following. That z minus z naught is equal to x naught, y naught, plus partial derivative with respect to x at this point, times the change in x, plus partial derivative with respect to y, times the change in y. So we're just accounting for changes in both variables, using and multiplying those changes by the appropriate partial derivatives. So it's important to see how this equation for a tangent plane relates to this equation of a tangent line. You have a function value plus derivative times change in variable. It's just that now you have two of them. And this right here, this is LF of xy, the linearization of f at x naught, y naught. Let's step through an example of that. 2x squared y plus 3y squared. And our point of tangency is 1, 1. So to get the linear approximation of this function at this point, we need, so that's going to be f of 1, 1 plus partial with respect to x at this point times a change in x, so we're going to have x minus 1 here, plus partial with respect to y times a change in y. So everything's skewed around this point. So in order to complete this, we need the partial derivatives. So, practice your partial differentiation. So what is derivative of this function with respect to x? Be careful, treat y as a constant. So we have 4xy from this, and then this contributes nothing because it doesn't depend on x at all. So that means that the partial at 1, 1 is going to be 4. What about partial with respect to y? So you get 6y from this term. Here, x is treated as a constant, but you still got a y sitting there. So it's just going to be, so it's like when you differentiate a function as a constant times x with respect to x, you just get the constant. So that's what you get. Fy is 2x squared plus 6y. So we evaluate that at 1, 1, and we get 8. We want to evaluate the function at 1, 1, and that's just going to give us 5. So we fill in everything we have. It's going to be 4x minus 1 plus 8. Y minus 1. So this is a linear function that approximates f near this point. Now, let's take a look at how good a job it does. And the way we'll do that is we'll pick a couple points that are near 1, 1. We'll evaluate the function at that point, evaluate the linearization at that point, and we'll just compare the two. Let's suppose we have f of 1.1, 1.1. So just add 0.1 to each, and what we get is 6.292. Whereas if we plug in those same x and y's into the linearization, we get 6.2. So the error is 0.092. Get 1/10 closer in each direction, so 1.01, 1.01. So if we plug in these same points into linearization, we get 5.12. So now the error is 0.000902. So what I want to point out is, along each direction, we got 1/10 as close to what with 0.11 with this one. But what happens to the error? It decreases by roughly a factor of 100. The error decreases quite rapidly as you approach the point of tangency. Let's do another, but in this case we use linear approximations a little differently. Suppose you have a cylinder, and you measure the radius, and you measure the height, and the values that you get are 5 centimeters for radius, 10 centimeters for the height. Compute the volume, pi r squared h, which in this case will turn out to be 250 pi cubic centimeters. Now, to ask this question, these are measurements. Measurements could be erroneous. So what if the measurements of r and h are off? Based on whatever instrument we're using, at least we have an idea of how far off they could be. Suppose they're off by at most 1/10 of a centimeter. If these measurements could be off by that much either way, what is the maximum possible error in the computed volume? Because what's going to happen is whatever error we have in r and h is going to be propagated by this formula. So a linear approximation can give us a ballpark as to how bad that error can get. So the linear approximation is going to be the volume at radius is 5, height is 10, plus partial with respect to r times the change in r, plus partial with respect to h times the change. So now this value here, this is an approximation of the actual volume at r and h. And what that means is the error, which is equal to the actual volume minus the volume we originally computed, roughly is equal to the linear approximation. It's just going to be these last two terms here. So all I'm doing is I'm subtracting this from I'm moving this to the other side. So all I got to do to estimate the error is compute this, or at least get an idea of how big it can get. So for that, I need the partial derivatives of v with respect to r and h, and I'm going to evaluate them. Actually, let me fill in where these things are being evaluated. 5, 10, r minus 5 plus dv dh. Again at 5, 10, h minus 10. And I know that these, r minus 5 and h minus 10, the largest they can be is 0.1 in magnitude. So we're going to assume that. So given that formula for v, what is dv dr? And then we'll plug in r equal 5 and h equal 10, so we're going to get 100 pi. And dv dh by r squared. So r is a constant now and h is a variable. So dv dr at 5, 10 is going to be 25 pi. So now we can fill these in. Now error can be positive or negative. It's the magnitude that we care about. So the error is going to be bounded by this derivative, dv dr, which is 100 pi, times the maximum possible change in r, which is 0.1, plus 25 pi, again times 0.1, the maximum possible change in h, that's a 0.